Hello, this is Mr. Mitchell. We are looking at section 1.5, analyzing graphs of functions. We've got a few notes here just to fill out. In terms of definitions and things, I'll let you copy those. I'm not going to read through all of this, so I will pause for a moment. If you need more time, you can also pause the video. So again, just some definitions and things that we need to be aware of. So we need to find the zeros of a function. We're going to find zeros. So we can do it with a calculator, or we can do it algebraically. Anytime you're trying to find zeros, you set the equation equal to 0. Oops. So how do we solve when we set things equal to 0? It's a quadratic, so we're going to factor. What multiplies 3x squared? 3x and x. What multiplies to 10? It's 10 and 1, or 2 and 5. You have to get 1 out of the middle here. So I think it's going to be more difficult to use 10 and 1 and to get 1 out of the inner and the outer term. So it's probably going to be the 5 and the 2. If I'm wrong, then we'll just use 10 and 2. So do I want a 5 and a 2 or a 2 and a 5? Well, if I put the 5 here, that's going to make 15. That's probably not going to happen. So it probably needs to be a 5 here and a 2 here. Signs are different. Bigger one's positive. So out of this is 6, this is 5. That means the 6 has to be positive and the 5 has to be negative. And then you finish by solving. Set each of these equal to 0. So x equals 5/3 and x equals -2. Okay, we're going to find the zeros here. So we're going to set it equal to 0. And then we got to solve. So how do you get rid of a square root? You're going to square both sides. You still get 0 over here, but now your square root is gone. I'm going to add the x squared to both sides. And I'm going to take a square root. So be careful here. This is where students make mistakes. It's plus or minus square root of 10. And it doesn't say round my answer, so I'm going to leave it like that. If later I find out I should type it in the calculator, I will. Okay. Again, I'm finding zeros, so let's set it equal to 0. So if you want to think of this as a proportion, you can cross multiply. So what happens when you multiply 1 times 2t minus 3? You get 2t minus 3. When you multiply this, you get 0. Essentially, when you have, this is called a rational function. Essentially, when you have a rational function, you just set the top equal to 0, which is what ended up happening. So you solve, you get 2t equals 3, and t equals 3/2. So it's finding your zeros. We could have also graphed them on our calculator and found out where they cross the x-axis. We can get more practice of that later, but we wanted to focus on the algebra method here. So vertical line test, we have to graph to do the vertical line test. So I already have them all typed into my calculator. I'll pause for a second so that you can type those in. When you're typing in the first one, that plus or minus, you do have to treat it like it's 2 separate equations. Our calculator does not do plus or minus as one thing, so do the positive square root of x plus 1, and then do the negative square root of x plus 1. So you don't have to have them all typed in. Notice I've turned off my other equations, so I don't have to graph them all at the same time. So when I hit graph, the red and the blue are together. They're not separate equations. They are the same. So does it pass the vertical line test? No, that means it's not a function. So what I would do for notes purposes here, I am going to use my calculator, but I'm just going to draw myself a little sketch here to remind myself what it looked like. And this is not a function. So it's not a function. It's a sideways parabola. And we go back to our calculator. So just to kind of show how to do this, you don't have to type in and retype everything. If you turn them off, there's no cursor on them. Right now, if I graph, I'm not graphing anything. But if I want to turn on this third equation, is the one I want to look at now. Oops. I go over here to the equal sign and I make sure that it's shaded in, it's darkened, selected. Then I'm going to graph it, and that's what it looks like. So does it pass the vertical line test? Can I draw a vertical line that touches the graph more than once? These, I know they come off the screen, they never go straight up. They always continue to go wider. So it does pass the vertical line test. So on my paper, I'm just going to draw a little bit of a rough sketch. Kind of looks like this. Again, we're just looking at this so that I can know for future reference. So this is a function. Sorry about that. Okay, this one is called a piecewise function. Our calculator can't graph the condition very well. These are conditions. So we're going to graph both of them at the same time. So I'm going to go back to graph. I'm going to turn off this other one, and I'm going to turn on these two. So then I hit graph. So I got green and pink. So both of these do not happen exactly at the same time everywhere. So we have to imagine that certain pieces aren't being used. So when I look at my first one, the negative 2 x plus 1, when I look at the pink graph, what's the condition? The condition is less than or equal to 0. Again, we look at our graph. So on the pink graph, we're going from x is 0. We're going from here. We're going from here this way. Here this way. So I really only want this piece of the graph. Okay? So you got to imagine we're just keeping this piece right here. We're not keeping this pink piece over here. All right? So when I look at my other equation, 2x minus 3, we want it from greater than or equal to 2. So we want the green graph from here this way. So we want this piece, and then we want this piece. So if I were to draw that on my really what I have this, and then I have this. Okay, you have your x and y axis. This is the green graph. This is the pink graph. We excluded pieces of it. That's why it's called a piecewise function. These are conditions. So these are the pieces I'm keeping. Does that pass the vertical line test? Yes, it does. If I didn't have these conditions, go back, forget about the conditions. Do the green and pink graphs pass the vertical line test? No, they would not. They would touch if you drew a vertical line. Remember, I'm drawing a vertical line to see if it touches. If there were no conditions, yeah, I hit the graph here and I hit the graph here. It wouldn't be a function. But because I have a condition, I have certain conditions that need to be met. When I get rid of this other stuff, the graph ends up looking like this. It's almost like a V, except for there's a space in the middle that's missing. Okay. We're going to skip increasing, decreasing for right this minute. We're going to go to relative, minimum, and maximum. We're going to use our calculator again. Figure we might as well go straight to that. So I need to graph that. So instead of erasing, just to show that I can get a whole bunch of equations in here, what is it, 3x squared minus 4x minus 2. And so then I graph that. And it's this orange thing in the middle. I'm sorry, I should have turned off my other graphs. Instead of erasing them, just turn them off. That way you don't have to retype them in. If you just turn it off, you can keep a whole bunch of graphs in there. So there's my graph. And what I'm looking for, we're not looking for the vertical line test. It does pass, it is a function. What I'm looking for, are there any turning points? Are there any inflection points? So what I can do, I think I need to zoom in. Our calculator does a lot of good stuff. I need to zoom in on this piece right in here somewhere. See how it's kind of, it's hard to tell whether that's an inflection point or not, whether that's a critical point. So we can zoom in one more time and see if that tells us anything else. So it doesn't look like it's going up and then coming back down. We can zoom in just one more time to be sure. Yeah, so it doesn't look like we have any relative mins or maxes here in terms of turning points. Okay, so not being able to see anything more, I'm not sure that we have an inflection, a local min or a local max. Because if you look at the overall graph, you might say, well, how do you go back to normal? Well, go to window, make your mins -10 and your maxes 10 for the x's and the y's. And if I graph it, then it goes back to normal. Okay, so there's my graph. I don't think I have a local min or a local max. So relative minimum, well, relative maximum. So for this, I'm going to say no relative min or max. So let's try to graph the other one. I'm pretty sure the other one's going to have a min or a max. So it's negative, what was it, x squared? Negative x squared plus 5x minus 10. That's the right equation. Make sure, always double check. No, minus 10. See, I would have had it incorrect. And then I'm going to turn off my other equation. So don't want that one on. So we graph, we're going to have a local max here. The graph does not have a min, it goes down forever. It's going to have a local max here. So we go to second calc is where you can do your mins and maxes. You have to know whether it's a minimum or maximum point. If you select the wrong option, then it's not going to work. So this is the point that I'm after. So it says left bound. You just have to be to the left of it. It doesn't matter how far. You just have to know the difference between your left and your right. Go to the right. How far to the right? It doesn't matter as long as you are to the right some. Then it asks you to guess near the point. So our maximum, when it does something like this, that's just 2.5. So our maximum is 2.5, comma, negative 3.75. So we can record that. Negative 2.5, 3.75. Make sure I recorded that correctly. Oh, got my negatives backwards. So it's negative, no, it's positive 2.5, negative 3.75. So we can do this with all kinds of different graphs. If just a hypothetical here, if I drew a graph and it looked like this, we've got a whole bunch of stuff going on here. We've got, this would be, and again, I don't have any coordinates labeled, but this would be a local max. This would be a local max. This would be a local min, and then this would be a local min. So you would need to find all of those with our calculator, finding local mins and maxes. So a graph can have many turning points. The higher the power, the more potential it has to have turning points. And if it's x squared, it can only have one turning point. Okay? If you have any questions, let me know. I will put the other problems up in a separate video.